I will introduce Dr. Lianjie Huang from Los Alamos National Laboratory. He's a senior scientist there, and he will be talking about passive seismic monitoring, a tool that he and a colleague of his has developed. So, colleagues, sorry I've developed, so I pass it off to you. Thank you.
Thank you, Bob, for your introduction. And do I share the right screen?
That's great.
Yeah.
It's great. Thank you. So thank you for sticking to the last talk. And this will be last tool we are going to discuss today will be optimal design of a microseismic monitoring network. And I'm Lianjie Huang. And I would like to thank several of my former postdocs working on this tool. And also I would like to take this opportunity to thank several colleagues in other national labs testing for their careful testing the tool and provide feedback that improve the tool. And also I would like to take this opportunity to thank my colleague in Los Alamos, Xiaoping Chu, for helping us to compile the code and generate a executable file in Windows OS. So today I'm going to discuss this tool for optimal design of a microseismic monitoring network and using the surface or borehole geophones for cost-effective microseismic monitoring at geological carbon storage site. And also this tool can be used for other microseismic monitoring applications. One second, okay. And then I would like to show the example application of the tool to the Farnsworth CO2 EOR field in Texas. And that's a field demonstration size of the phase 3 of the Southwest Regional Partnership on Carbon Sequestration. So the tool basically is for optimal design of the microseismic monitoring network to reliably locate into microseismic event cost effectively. So, for example, in this example, what we want to do is try to understand the relationship between the microseismic event location, as shown, for example, in this monitoring region, and within the target monitoring region, and the geophone distribution. So, for example, here, this is a surface we design area, and this is a blue triangular at a surface seismic station. And these are borehole geophone, can be multiple borehole, one borehole. And you can design a target monitoring region, for example, like near the reservoir region, or a particular fault, and just define whatever you want to monitor, target monitoring region. So as I mentioned previously, this tool is applicable to any geological carbon storage site and other microseismic monitoring applications, and can use both a surface seismic station and all borehole geophone arrays, in combination or separately. So this tool is the GUI of this tool is designed by Metric. Is this company, and then using our executable file. So the tool can be run on Linux, Windows, and Mac OS. So it's basically most of the OS available today. And the GUI is based on Java. So you run the tool basically just using this command to run the tool. So it's very simple. And then when you run the tool, you show up if you need some information, and by click the button, and you can pop up information you need. For example, this is acknowledgement, this is a reference. So start, for example, in 2014, we present this idea, and then we have an application to one of the CO2 monitoring injection field. And then, we also apply to geothermal. That's a EGS Colab. That's using multiple borehole. And this is a demonstration using Kimberlina CO2, Kimberlina 2 model. So if you need a menu, you click that button, menu button, and we show up this menu, and then it describes how to use the tool in detail. So the tool, the first interface like this, so that you need to go through step by step by clicking into parameters, and then you enter, a lot of parameters, and you define the geographical distribution region and monitoring region, etc. Can be entered through the interface, or you can define yourself, and then can input a file, and that can be any kinds of the region, for example, any kinds of distribution. And then you click save, and then can run, and then automatically run. During, when you run the tool, and then will show up, will pop up a progress bar, show the job progress. And these normally run on a desktop a few minutes. And then when it's done, it will plot the result automatically. And if it doesn't, you can just click here to plot the result. Or if you want to replot the result, you can click here. And here is just an example of the output. Basically, we enter the 3-layer using this tool, 3-layer model. And then you show now here, basically, this is the standard deviation error of the microseismic event location. And this basically is a number of geophone, we use during the calculation. And then it shows that there is a suddenly change here. So this basically indicate that a surface seismic station are needed for cost-effective monitoring for these kinds of, for this example. So next, I'm going to show you an example application of this tool to the Farnsworth CO2 EOR field in Texas. So this is a location here. We show here, and that's the North Texas. And many people should know that. And then this is a pipeline, CO2 pipeline. So in that region, geology show there are two major faults. One is a horizontal here, and one is along this one, north-south, and then this is east-west, along east-west. And this injection, one of the injection well, and at that time, basically, decided approximately target monitoring region will be this circular region. So we defined this model on the right here, and this red basically show is the reservoir monitoring region, as I show next slide here. And this cylindrical region basically along the monitoring well is a radius about 1.6 kilometer from the monitoring well at the center here. And then there is a depth. You can define whatever your target monitoring region, the depth. Region, for example, here is from 1.2 to 3 kilometer, and that's up to the basement. And also, the fault, you can define that these are two faults, and then you can, this start point, basically the microseismic event that we use for synthetic microseismic data generation. And so here, basically, what we use is about 1,700 synthetic events for the reservoir, and then for the fault, about 500 synthetic events along the fault, two-fault plane. And then we invert the location and focal mechanism of the synthetic event and compute the standard deviation error of location between synthetic event and location and in inversion result. So, in this example, basically, we design for surface monitoring, using surface seismic station. So the monitoring region is on the surface is about 5 kilometer by 5 kilometer region, as shown here. And then So when we do the calculation, basically we use here n by n, and then n is varied from 4 to 49 regular distribution. And then we can calculate the standard deviation error of the event location. We use a Gaussian distribution error of the standard deviation travel time peak, and velocity error basically 25 microseconds. That's in the travel time peak, basically using a Gaussian distribution of the error in the peak during the calculation. So here is the result, basically output from the tool. It shows that it requires 9 surface seismic stations to monitor the microseismic event within the reservoir. So 9 stations corresponding to here. So the standard deviation error of the event locations about 21 meters. But if we use a 16, as shown here, the standard deviation error of the event locations about 16 meters. So reduce a little bit. So that also depends on the accuracy requirement during the monitoring. So here is a result of the monitoring for the fault. So for monitoring microseismic event on the faults, the 2 faults require 16 surface seismic stations, and the standard deviation error of the event locations approximately 17.5 meters. And our code also we can do the calculate the focal mechanism error. So we calculate both the reservoir and the fault, and we show that it's about approximately 25 surface seismic stations need for focal mechanism inversion of a microseismic event in the reservoir in the fault, in fact. And for standard deviation error is approximately 4 degrees for double couple component and about 5% for non-double couple component. So this is both one for fault, one for the reservoir, and the error is a little bit different for the fault. So the tool can output the exact location, all these, defined for about 25 stations, and then what's the location in the space on the surface. And in the reality, basically, you cannot just put those seismic stations because of some surface condition and accessibility of the surface. So here it is a modified plan based on the guideline of the output from the tool. And then this is adjusted based on the accessibility of the surface condition. And then we can use this distribution to recalculate the error. So it's about 15, 17 meters. And then the focal mechanism also is a similar error. So that means that this is accessible. So in summaries, we have these two available for optimal design of a microseismic optimal design of microseismic monitoring network. So this tool is available through NETL EDX. So the tool can be used for for monitoring for geologic carbon storage and also other microseismic monitoring application. So this is in order to access the tool, in order to download, you need to first register through the EDX. And the example application of the tool to the functional CO2 EOR field show that 9 surface seismic stations are needed for microseismic event location in the reservoir, and 16 surface seismic stations are needed for monitoring microseismic event in the fault. And 25 surface seismic stations are needed for focal mechanism inversion of the microseismic event in the reservoir and fault. And focal mechanism inversion, this capability is not included in current release of the tool. And thank you for your attention.
Hello. Hello, this is Bob. Sorry, I went on mute and accidentally hung up. Thank you, Lianjie. Were there any questions in the chat?
We have one from
Okay.
Preston Jordan. When will the
so-
focal mechanism be available?
Yeah, so that will be depends on the future release. Maybe Bob can answer that, if we want to continue have a future release.
Yeah, I think you and I would need to catch up and discuss the status of that and try to figure out what the review process would be. So I'm not sure we can comment right now on the timeline for that. But again, knowing that that's of interest, I think is useful. Yeah, so I was going to ask a question. So this is a design based on a specific, on the Farnsworth site. Is this something that, were geophones deployed at this site based on an optimized design? Is this something
Yeah, so that geophone was deployed and then recorded since, I think 2 years ago. Okay. Yeah, and then, yeah.
So this is an application where the tool was used to design the monitoring at the site?
That's correct.
Okay.
That's correct.
Yeah, that's
initial when before they deploy, we designed these, and then they deploy based on the location I show at the end. Modified from our design guideline, and then because some service station, even based on our design, some location exactly and some facility, for example, and maybe on some field that may not, for example, maybe because it's a service of the farming area, so may not accessible, so need to move a little bit, and that's a final deployment at the field.
Okay.
And it's called TAT deploy that, yeah.
Okay, thank you.
Mm-hmm.
Are there other questions for Lianjie? Okay, well, we are well ahead of schedule, but we are going to continue on, and I think the last thing to do is just open it up for discussion. We still have about 85 participants, but we could try to take those questions either by typing in the chat or just by unmuting and see if that becomes too chaotic. I'll stop and see if there are any thoughts or questions. Well, in the meantime, I'll just mention that, we did have 10 tools at the end of phase 1 of NRAP. We now have, right now, I think 6 tools that we've presented on. This is not really a reflection of a reduction in the capability. I think just want to note that several of the tools that were developed in phase 1 have, been incorporated into, for example, the integrated assessment model now, sort of embodies several of those pieces of functionality, or some of that functionality is still being incorporated, but it's not that there is a reduction in the number of tools doesn't correspond to a reduction in the capability. In fact, I think we've substantially expanded the capability. Okay, there's another question from Preston. Thank you. Did the Kimberliness scenario include the uncased, unplugged wells? Or rather unplugged up to or below the base of the USCW. Uncased borings, yeah, rather than wells. And I'll defer to anybody else from the NRAP team who's on who wants to comment on this. I think the representation of the wells in this scenario, and I was involved with this for an earlier study, and I've been less up to date on this recent application. I think it's based on model representations of the well as a cemented well using, if I'm not mistaken, a multi-segmented analytical model of the well behavior. I think it is not looking at that scenario of a completely uncased boring, which would be obviously a worst case scenario for a leakage pathway. We certainly do have a model that handles, it's a drift-flux model that handles open wellbore, open boring, I guess is the right word, leakage. That has not been applied in this case to my knowledge, but could be.
So this is Erika Gasperikova from Lawrence Berkeley Lab, and I may add to that that the work that was done for the multi-well scenarios actually used the source from Dogger. So however the wells were classified in Dogger database, there were used input for the analysis, but within that analysis, the risk or identification which wells are most prone to leaking was done within that I guess part that we haven't presented here. So I don't know, Preston, if I answer your question, but the wells were basically the wells that were used had a higher probability of leaking, without specifying if it's uncased or cased.
And your next question, your following question here, Preston, about the physics that's incorporated in the drift flux model, the open wellbore model. I think you're right. We've been having this discussion recently that the assumption is not a drilling mud in that boring. So there was some discussion about how we would modify that model and to account for that, with possible applicability to even area of review type questions. I think that is, again, has been discussed recently and may be a valuable addition. We'll follow up with you to get your thoughts on that.
And thank you, Preston, for clarification. So the answer is no. All wells were cased then.
Okay. Are there other questions, comments? If there are thoughts on valuable applications or field studies or data sets that would be available to continue to refine the methods and the tools, the recommended practices and the tools that we're developing here, if there's anybody who's interested in gaining access and feel like they're having difficulty gaining access to the NRAP tools and the recommended practices, just encourage you to reach out. You can reach out to me directly. You can reach out to, I think, Chris Wyatt and Mia Serrata. You can use the portals that I showed you before to access the existing application catalog. You can the tool user forum. These are all viable pathways. Hopefully, you will find them to be useful, and we do encourage interaction and feedback.
Bob, this is Mike Nicholas. I just wanted to thank you again for putting this NRAP training on, or workshop on. I think we all look forward to continued testing and deployment of these tools. And I'm hoping we can do this again as you guys move forward, you folks move forward with these.
Thanks again, Mike. And I want to thank everybody at GWPC for being very accommodating and giving us this venue. And thanks to everybody who's joined for your time. And please don't hesitate to contact us. Thanks very much.